Okay, now let's move on to problem 3. So problem 3 is another longer multi-part problem. And so I'll start again with just the setup with the assumptions and the system and the table and everything, and then we'll move on to the solution after that. So for problem 3, we have refrigerant 134A that's contained in a rigid tank at a total volume of 1 cubic meter at a temperature of 20 degrees Celsius and a quality of 10% at state 1. Then a leak develops at the top of the tank such that the saturated vapor slowly escapes from the top of the tank, and then the leak is stopped when all the liquid inside the tank has evaporated and only saturated vapor remains at state 2. Heat transfer occurs such that the temperature remains constant during the process, and data for the refrigerant is included in the table below. Okay, so this data in the table below, just a quick note on this. This is what they're talking about down here. And this table is actually just a cut of our SLVM table. And so it looks a little bit unfamiliar maybe because we're more used to seeing our SLVM tables in a format where they give us temperature and pressure, and then they have a section for liquid with VF and then UF and HF, and then they have right next to it in red a section for vapor. And so in that case they have VG and UG and HG. But these are the same things that appear here, just in a different format. So VF would be what we usually see over here in our normal tables, and then VG would usually be what we see here in our normal tables, but they're right next to each other here. Same thing for internal energy. This is what we would usually have, but now they're just next to each other. Same thing for enthalpy as well. So the point is, just don't be intimidated. Just make sure you look at what this table is giving you and understand that this is maybe the way that you're more used to seeing it, but it's the same information. So just make sure you get your information right, look at the subscripts here, and that's all we need to worry about there. So now let's get into talking about what's happening in this problem. So we have this tank here, and they give us this schematic that we can draw our system on. So we have this tank, and it has some R134 inside, and then at state 1, they give us these properties, and we just have the substance sitting inside the tank here. But then, immediately after state 1, some saturated vapor starts to leak out of the top of the tank, and so some mass is going to leave the system, and then we will have a lower mass at state 2 with some different properties. And so we can draw the system on this diagram here. So the system that we should focus on is going to be the R134 that is inside the tank. So I will write our system is going to be the R134A in the tank. And so we're only focusing on the mass of R134A that's inside the tank at any given time, because there's going to be some mass leaving the system, but at state 1, we're focused on the amount of mass that's in here at state 1, and then we look at what's the net change from state 1 to state 2, and so we're really only focusing on what's inside the tank at any given time. And I always like to fill out a table, so they give us some of those properties right here, but I just like to kind of summarize everything in a table here. And so let's talk about what properties we need to keep track of. So we'll need to keep track of what's happening at state 1, what the properties are here, and also at state 2. But then for these transient open system type of problems, when you have some sort of inlet and exit, here we only have an exit, but it's good to keep track of what are the properties at the exit. So this is kind of getting into our assumptions, but we basically assume that right here at the exit, we have one uniform property value that we're going to report. And that's the properties for saturated vapor at this TE equals 20 degrees Celsius. So we keep track and we say that there's one property value that we report here for the values of enthalpy or internal energy of the fluid when it's leaving the tank. So it's taking some energy out with it, and we just report that one value here at the exit. So we're also going to want to keep track of what's happening at our exit. So the first thing that they give us is temperature in degrees C, and they give us the temperature. It's actually the same at all the states, at state 1, state 2, and at the exit. It's always going to be 20 degrees C, so that's easy for us. 20 degrees C the entire time. And then they also give us some information about quality here. So they tell us that X, our quality, is going to be 0.1 at state 1, and then they don't give us explicitly an X value at state 2, but they tell us that we have saturated vapor, and we need to remember that saturated vapor means X is equal to 1.0. So if we had saturated liquid, that would be X equals 0, but they're telling us we have saturated vapor, so we can infer that the quality is going to be 1.0. And the same thing is true at the exit. We also have saturated vapor leaving the system right here. And so that is going to be a quality also of 1.0 at the exit. Okay, so that's all they give us in terms of our properties for now, but we can leave some room in our table to come back to. And so let's draw on our system diagram what energy and work interactions we have. So work is easy because it tells us we have a rigid tank here. So we need to remember that rigid tank means that our work is going to be 0. So we're not going to draw any work here because the walls of this tank are fixed and they're not moving. So the fluid can't do any boundary work like it would in a piston cylinder problem. These walls are fixed and the fluid is not going to be doing any work on this, and then we don't have any external work. So we're not going to draw any work here. Then heat transfer, though, it tells us that some heat transfer occurs such that the temperature remains constant during the process. So that means we're going to have some heat transfer Q going into our system. And it's going to be going into our system because as this fluid leaves the system, it's going to take some of the energy in here outwards with it. And so, the temperature would naturally want to drop of the fluid in here. So if we supply some heat into it and basically replace that energy that's being taken out, then we can keep our temperature at that 20 degrees Celsius from state 1 to state 2. So that's all we have. Oh, but then we also need to draw our mass flow rate going out. So I'm just going to write m dot out here. And that's all we have with our system. And so let's get into our assumptions. So we already mentioned we have a rigid tank here. So the walls of this tank aren't moving. And that means that our work is going to be 0. So we're going to assume rigid tank, meaning that our work is going to be equal to 0. And then again, like we said, at the exit, we're basically assuming that we have uniform properties, uniform flow also, so everything's coming in one-dimensionally and uniform at this exit here. We don't have to worry about any velocity profiles or gradients or anything like that. So we are going to have uniform 1D flow at the exit. And then we also don't have any information about any velocity or any changes in potential energy. So we can also assume that our changes in kinetic energy and our changes in potential energy are going to be equal to 0. And that's really all we need for now for our assumptions. We don't have anything like steady state in this case because we have some mass leaving the system. So the properties of this R134A are going to be changing over time. So we don't have steady state or anything like that. So this is basically all we need for now. And so I'll jump into the solution for part A. Okay, now let's move on to our solution for part A, which asks us here to calculate the mass of the refrigerant escaping from the tank and to report our answer in kilogram. So we want to find the amount of mass that leaves the tank through the leak here in the top. So we're not given any information directly about the mass at either of the states, but what we do know is that we have a total volume of 1 cubic meter, and this is a rigid tank. So this volume is going to stay the same the entire time. The total volume in here is going to be the same since the tank is rigid. And we can remember that we can calculate the mass, I'll write this in the equation section, at any state by taking the total volume at that state divided by the specific volume at that state. So we don't have any information directly about specific volume, but what we do have is the quality at both state 1 and state 2. And we can use that quality directly to find the specific volume at each of the states. And then we'll be able to solve for our mass at state 1 and state 2, and we can take the difference to find the amount of mass that leaves. So let's scroll down to the equation sheet and look at those equations that we'll need. So the first one here is conservation of mass. I was talking a little bit about it, but let's actually figure out how we apply conservation of mass here. First of all, we don't have any mass coming into the system because we just have mass leaving the tank here. And so we can just integrate both of the terms here. We don't have a sum, we just have one m dot out. But if we integrate that, then we get the form m2 minus m1 should equal a negative m out. Right, negative sign because we're subtracting it here in our equation, and then this will be our delta m that we get from integrating this term. And so, like I said, we can use specific volume at each of the states to find these two quantities, and then that will give us our total mass that leaves the system. And so the only other equation that we need here is our quality equation that you see here. We have this relationship that we can find any property at a mixed state with just the quality, and then these properties of the gaseous and fluid states. And so we can just basically plug in our V for our property. So we'll just say that Z in this case is going to be equal to specific volume for us, and then we can just plug that in here and find our specific volume at the mixed state. So I will go up and write those in our equation section. So we have our first law tells us that m2 minus m1 should be equal to a negative m out. And then we also have Z, well, I'll write Z at a mixed state is equal to x zg plus 1 minus x times zf. And those are the only equations that we need. So first of all, we can use this, like we said, to find specific volume at states 1 and 2, and then we can use that to find the mass. But at state 2, we have a quality of 1.0, and whenever we have a quality of 1, then this term here goes away, and so we just have our V mix is going to be equal to our VG, which we're given here in our table. So, when the quality is 1.0, our V, whenever V2 is going to be equal to the specific volume when you have a quality of 1.0, which is just going to be equal to VG. And so we'll say that V2 is equal to our value here of 0.035997 meters cubed per kilogram. And then we can use that to find the mass at state 2 using this equation like we said. So we can just do that right now. Our mass at state 2 is going to be equal to our volume, our total volume divided by our specific volume at state 2, which is going to be 1 cubic meter divided by 0.035997 meters cubed per kilogram. And so this should give us a value of M2 is equal to 27.8 kilograms. Great, so that's our value for M2. So we are almost there. We just need to find the value for M1, but we need to use this quality equation to find our value for the specific volume at state 1. So let's plug that in here. We'll get that V1 is equal to X1 times Vg plus 1 minus X times X1 times Vf. And if we plug in our numbers here, X1, remember, is 0.1. So we get 0.1 times, now Vg we can get from the table again, 0.035997 meters cubed per kilogram. And this is plus 1 minus 0.1, right? That's just our X1 value that we get from the table, times Vf. Now we can get this from the table as this value right here. So that's 0.0008161 meters cubed per kilogram. And so if we plug this all into our calculator, we should get V1 is equal to 0.00433 meters cubed per kilogram. And then we can do the same thing that we did before and solve for the mass at state 1, but now using specific volume at state 1. But this total V is going to be the same because we have a rigid tank. So now we will have M1 is going to be equal to V over specific volume at state 1, which is going to be 1 meter cubed divided by 0.00433 meters cubed per kilogram. And this should give us a value of 231 kilograms. So quick sanity check, our mass at state 1 should be bigger than our mass at state 2, right? Because we have a total mass of this much before, and then some leaves the tank, and so that gives us a smaller amount of mass at state 2. And then we can just take the difference to find the amount of mass that left. So we could just use this equation that we got from conservation of mass. I'll just rearrange it by moving the negative to the other side, and we just get the amount of mass out of the tank should be equal to M1 minus M2, which should be equal to 231 kilograms minus 27.8 kilograms, which should give us a value of 203 kilograms after we do our rounding. So this should be our answer for part A. Now let's move on to part B of this question, which asks us here to find the magnitude of heat transfer during the process and to report our answer in kilojoules. So whenever I'm asked to find heat transfer, usually the first thing that I think about is First Law, our conservation of energy equation. And for this part of the problem, that's all we're going to need to solve for the heat transfer. We have some information about some useful properties here that we can use, and we know that this is a rigid tank, which means that there is no work. So we're able to just relate our heat transfer to our changes in properties. So let's scroll down to our equation sheet and look at First Law. So our First Law equation is right here in the differential form, and we can start just simplifying things out based on what we need for our problem. So we know that there's no mass coming into our tank, so this whole term is going to go to 0. And then also we said that it's a rigid tank, so there's no work. And then we're also neglecting changes in kinetic and potential energy, so these terms drop out. And this is all we have left. So we can just integrate the remaining terms, this change of energy, this m dot times this enthalpy term, and our q dot term. And I'll write out what we get when we simplify this up here. So the simplified form from this dE dt, we're just going to get a delta energy. Change in total energy is equal to then this term down here will be just a mass times an enthalpy value. The dot goes away, and we have to keep this negative sign here, so this will be equal to the negative mass out of the system times the enthalpy at the exit, or the enthalpy at the outlet here. And then for our Q term, our dot is just going to go away, so then this will just be the total heat transfer Q. And then we can also remember here that our total change in energy, delta E, is going to be comprised of changes in total internal energy plus changes in total kinetic energy plus changes in total potential energy. But we're neglecting these two terms, so what we're left with is just a delta U. So I'll write that form and just rearrange for Q. So we get Q equals delta U plus M out times H out. And then finally, we want to break up this big delta U into terms that we can actually evaluate, and we can do that by remembering that total internal energy is equal to mass times specific internal energy at any given state. So if we want to find U1, then it's just the mass at state 1 times the specific internal energy at state 1. Same thing for state 2. So we can actually write this out again as Q equals M2U2 minus M1U1 plus M out H out. Right, because with this delta we get final minus initial. And so this is the final form of our first law that we are going to use, rearranged to just solve for heat transfer. So we have all of these things. The masses for M2, M1, and M out we just solved for in our last part of our problem. And then these properties we can find either with the quality or just knowing that state 2 and the outlet state are both at the saturated vapor state. So we can find all these properties here. So this is all we need for this part of the problem. So I will go up and write that. I'll write it in the equation section. Generally, it's good to write out the whole first law or the whole basic equation that you need and then simplify it in this section here. But I'm just writing it out in the simplified form since I did the derivation down by the equation sheet. So this should be equal to M2U2 minus M1U1 plus M out H out. Okay, like I said, we already have M out here we found for the last part of the problem, and then we also found M2 and M1. I put those values in the table up here, and then so we just need to find what these properties are here. So first of all, we know that, again, at state 2 and at the outlet state, we have a quality of 1.0. So whenever we have a quality of 1 here, we have the saturated vapor state. So we can say that our V is equal to Vg. We saw that in the last part of the problem. And also U is equal to Ug, because this G is just the saturated vapor property. And that's what appears here in our tables. And also H is equal to Hg. I'll write that up here because this is the outlet state, also at saturated vapor, so H equals Hg. So we can say already, I'll just rewrite first law down here to be thorough, but we can write down the properties that we need at state 2 and the outlet state. So we get that U2 is going to be equal to Ug, which is going to be equal to, in our table here, 241.02 kilojoules per kilogram. And then also we know that H out will be our enthalpy at the saturated vapor state, because at the outlet we have saturated vapor. So that's just going to be this value in our table here, 261.6 kilojoules per kilogram. And the last thing we need to solve for here is our internal energy at state 1. And we can solve for that by using our equation for equality that we have here. But now instead of specific volume for Z, we're just going to plug in internal energy because we know the quality at state 1 is 0.1. So we can just plug that in here and get everything that we need. So I'll do that down here. So U1 is going to be equal to X1 times UG plus 1 minus X1 times UF, right? This is just this equation plugging U in for Z. So this is going to be equal to X1 is 0.1 times UG. We can get from our table here as 241.02. Kilojoules per kilogram plus 1 minus 0.1 times UF from our table here, which is this value, 78.857. Kilojoules per kilogram. So if you plug that into your calculator, we should get U1 should be 95.1 kilojoules per kilogram. And now we have everything we need to plug into our equation here, so we can just plug everything in and find the total heat transfer. So M2 we found was up here 27.8 kilograms. 27.8 kilograms times U2, right, which is going to be equal to 241.02 kilojoules per kilogram. And see that our units, the kilograms cancel out and we're left with kilojoules, which is what it asks us to solve for. So that's a good sign. So then we're subtracting M1, which is up here, 231 kilograms. 231 kilograms times U1, which we just found is 95.1 kilojoules per kilogram. And then we add our M out, which we found in the last part as 203 kilograms times the enthalpy at the outlet, right? We don't want to use internal energy. We want to use enthalpy here. So that's 261.6, what we found here. And so if we plug that all in, we should get our heat transfer is equal to 37,800 kilojoules. So this will be our final answer for part B. Now we're on to our final part of the problem, part C, which asks us to determine whether the heat transfer is into the system or out of the system. So back when we drew our system diagram, when we were setting up the problem, I drew this arrow for heat transfer going into the system, just kind of based on an intuitive guess. But I said it doesn't matter in your system diagram whether you draw your arrow going in or out of the system. The math will tell us what direction this heat transfer is occurring in. And so we did our math in part B, and we used this equation for first law and found a value for Q. And if we found that value to be positive, then that means that we have heat transfer going into the system. And if we get a negative value, then we know that that means that heat is leaving the system. So our arrow would point outwards. And it turns out that in part B, we got a positive answer for our heat transfer, as we just saw. So that means that we were correct in drawing our arrow pointing into the system, and that our Q will be into the system. So I'll write that out. heat transfer occurs into the system. And then you want to write some sort of justification. So I would just write because Q is greater than 0 here in part B. So this is our final answer, and this is the end of this exam. So the final answer here is into the system.